Hi everybody, Physics Ninja here, and welcome to my review problem set for AC circuits. What we're going to do today is we're going to look at 6 problems. There are 22 questions related to these problems dealing with all things related to AC circuits. We're going to focus mainly on series RLC circuits, look at things like reactance, phasors, peak voltages and currents, for example, the phase of the current relative to the voltage, resonance, and energy and power delivered and dissipated. All right, so here's what you do is you go to the description down below. There is a link there that is going to get you to the problem set that we're going to review in this video. Download the problem set, start working out the problems for yourself, and then you come back and watch the video. All right, physics is not a spectator sport. You need to work through some of these problems, try them out before you come and watch the video. Otherwise, you will have learned nothing. All right, like with all my videos, if you like it, give it a thumbs up. Consider subscribing to Physics Ninja. It is the best way to support what I do. All right, let's get started. All right, here is problem 1. We have a generator with a voltage equal to V naught sine of omega t is attached to the RL circuit as shown below. Our first question says, if the reactance of the inductor XL equals to the resistance R, what is the maximum energy stored in the inductor? All right, so for this one, you have to just think about how do you calculate the energy stored in an inductor? For that, you should know that it's 1/2 the value of the inductance multiplied by the current, okay, squared. So this is an important equation. Tells you the energy in joules if you measure inductance in henries and current in amps stored in that inductor. Now, since we're looking for the maximum energy, well, we need to find what is the maximum amount of current that is going to flow through this inductor right here. All right, they do tell us this, that the reactance equals to the resistance. So for AC circuit, you can calculate the maximum current as being that maximum voltage. In this case, it's E0 divided by the total impedance of the circuit. In this case, we only have a resistor and an inductor, so the total impedance is square root of R squared plus the reactance squared. All right, but now they told us that XL equals to R. Therefore, you simply go like this. We substitute XL for R, and you're going to get 2R squared down here at the bottom. We get E0. Take one of the R's outside of the square root, and this is what we have for our maximum current. So now you go back and you substitute to get the maximum energy stored. So you do L, and now we have our maximum current, E0 over square root of 2 multiplied by R. So what you just do now, take all the numbers outside and bring them to the front. Once I square the square root over here, I'm going to end up with a factor of 4 once I take care of all of these multiplications. I have L, and here I'm going to have E0 divided by the resistance squared. So that is the maximum amount of current, and that there corresponds to choice B. All right, next question says, if we decrease the generator frequency, the magnitude of the peak voltage across the resistor will do what? All right, so the key word here is that we're decreasing this frequency. Now, if you think about what the reactance is for the inductor, it's calculated as omega multiplied by L. So if I decrease the frequency, I'm making omega smaller, it means that this reactance is going to get smaller. Now let's think about what happens to that maximum current then. The maximum current, again, it depends on both the resistance and also that reactance term. But if I'm making the XL smaller, I'm going to be dividing by a smaller number. That means that the maximum current is actually going to increase now. If that maximum current increases, it also means that the maximum voltage across the resistor, which you calculate as simply the value of the resistance, multiplied by that maximum current. If I max goes up, VR max is also going to go up. Therefore, B is the correct answer. Next question says the generator frequency remains at its original value and a capacitor is added in series to the circuit. If the capacitor reactance XC equals to the resistance, how does the maximum current change? All right, so in order to calculate the maximum current now, you need to include this additional reactance term. And for AC circuits, for series AC circuits, this is how it looks like. The total impedance, which is the total term down here in the denominator, is R squared plus, this is XL minus XC squared. Now let's think about what happens to all of these terms. So we have XC, which is equal to R, and we also have XL that's equal to R. So those terms are going to cancel out right here. So at the end of the day, we're going to get our maximum current, which is the maximum voltage divided by simply the resistance. We can see that this number here of I max is bigger than the one we had over here in the previous case. Okay, so the current in this case is going to increase. B is the correct answer for that case. All right, let's go to the next problem. All right, for problem 2, we have consider the electrical AC circuit shown. It consists of a variable frequency AC generator providing a voltage VT which is equal to 18 sine of omega t, a 10 ohm resistor, a 15 microfarad capacitor, and a 24 microhenry inductor. First question says, to what frequency omega should the generator be set in order to maximize the peak voltage across the resistor? Again, the peak voltage across the resistor here, we're looking for the max, is simply equal to the resistance multiplied by that maximum current. So what we want to do here is we want to try to maximize that current. So what should we do? The current in this type of circuit is given by this expression over here. It's our maximum voltage of the generator, which in this case is 18, divided by the total impedance. Total impedance is R squared plus the difference of the reactance terms, like this. Now, how do we make Imax as big as possible? We're going to make Imax as big as possible whenever we are at resonance, and that is when XL equals to XC. If you set those equal to each other, you get, again, this is omega L, and the reactance of the capacitor is 1 divided by omega C. So if you solve for omega here, you're going to get the condition where we're going to be at resonance, and that is exactly what we're trying to solve here. So omega is 1 divided by square root of LC. So we go ahead and we substitute in all our numbers right here. We have the inductor, which is 24 milli, 10 to the minus 3 henries. And then we have our capacitor, which is 15 microfarad, that's 10 to the minus 6. We substitute here, and we should get something that is like 1667 radians per second. If you round that to 3 significant figures, we should have A as being the correct answer right here. All right, next problem says, the generator is now set to the resonant frequency of the circuit, so we know the omega. What is the maximum energy stored in the inductor at this frequency? Again, the energy stored in the inductor is 1/2 L, again, Imax squared. So we can calculate what the Imax is because it's very simple. If you go back to this expression, it is what that maximum voltage is simply divided by the resistance, and that happens at resonance. So now we can substitute this in right here. So we have 1/2 L, and now my Imax is Vmax divided by R, and just square that value. So now you could substitute in all our values. So we have 1/2, we've got our inductance, which is 24 millihenry, 10 to the minus 3. And here I put in what is the maximum voltage generated by that generator is 18. And divide that by the resistance, which is 10, and don't forget to square that. You put those numbers in the calculator, you should get 0.0, roughly 389 joules. That there corresponds to choice B. All right, and the last part over here says, with the generator set to the resonant frequency, what is the average power dissipated by the resistor? All right, so our average power now, you write it as this. It is 1/2. Again, the 1/2 is important right here because you're averaging over sinusoidal functions right here. It ends up being 1/2 R Imax squared. That is how you calculate the average power. And again, we are dealing at resonance right here, so we simply substitute our maximum current that we calculated. So I'm just going to do one last step. R, and this here is Vmax over that resistance squared. I can go ahead and substitute in all our values. We have 1/2. Vmax squared is going to be 18 squared. And then there's only going to be one resistance left over, so I'm going to be dividing that by 10. If I go ahead and substitute those numbers in the calculator, I think I should get 16.2 watts. So that there corresponds to choice B. All right, next question says the generator frequency is now omega, which is 1330 radians per second. Which element has the largest peak voltage? Well, if omega actually went down from the previous case, you should automatically know that the reactance of the inductor is going to be less than the reactance due to the capacitor. Okay, because XL is proportional to omega and XC is proportional to the inverse of omega. All right, we can actually calculate these two values now. XL is going to be equal to omega L. Use that new value and you should get 31.9 ohms. If you calculate what the reactance is of the capacitor, it's 1 divided by omega C, and here you get 50.1 ohms. Now, what I would say right here is I would probably also calculate what that maximum current is. And the maximum current is the maximum voltage divided by the total impedance, which includes all of these terms now, R squared, and then XL minus XC, and square all of that value. Now let's substitute in all these values. Here you get 18 for the maximum voltage. The resistance is 10. And then we substitute in over here. We're going to have 31.9 minus 50.1. I'm running out of space. Don't forget to square that whole term. All right, you calculate what this maximum current is, and you should get something around 0.866 amps. All right, now how do you compare the voltage across all these elements? Clearly the voltage across the capacitor is going to be bigger than the inductor, so I'm going to get rid of that one right now. The voltage across the resistor, again, I'm only looking at the maximum values right here. It's the value of R multiplied by I max. For the inductor, it would be XL multiplied by I max if I'm only interested in the maximum voltage. And for the capacitor, it's XC multiplied by I max. Now, look at all my reactance values. XC is the biggest one, so far this is the biggest number that we're going to get. I also have to compare it to the generator, however. The generator maximum is 18 volts, so when you multiply XC 50.1 multiplied by that maximum current, I am going to get a number here that is bigger than 18 volts. Okay, so the largest voltage is going to be across that capacitor. Nice problem. All right, next question says, with the generator frequency still here, what is the first time after T0 that the magnitude of the voltage across the resistor is a maximum? Well, let's write down an expression for the voltage across the resistor. Again, it's going to be R times I max. And now we have this sine function, omega t minus my phase angle. All right, now since this is more capacitive, this type of circuit, because we're dominated here by this reactance, which is 50.1 ohms, I am going to find that the current actually leads the voltage here. Current leads voltage. Now, if we calculate what this angle phi is, so again, the expression for the angle phi for a series RLC circuit looks like this. It's XL minus XC divided by R. Go ahead and substitute our values here. You should get minus 61.2 degrees. Now, when is this this voltage across the resistor going to be a maximum? It's going to be a maximum whenever this total angle here is equal to what? It's equal to 90 degrees, or I'll convert everything into radians right now, to pi over 2. This is when you're going to get the maximum value of the voltage across the resistor. So now what you want to do now is solve this equation here, omega t minus phi equals 2 pi over 2. So I know phi, I bring it to the other side, and then I divide through by omega, and I get my final expression here, which is pi over 2 plus the angle phi, and then divide this whole thing by omega. All right, we'll substitute in all our numbers now, pi over 2. Now plus, but the angle here was minus 61.2, so watch what I do. Minus 61.2, I have to convert that into radians, And then at the end, I need to divide through by omega, and omega is going to be the 1330 that we've been working with. 1330 radians per second. All right, now you substitute in all the numbers, assuming I didn't make a mistake. 3.78 multiplied by 10 to the minus 4 seconds. And that there looks like it corresponds to choice A. All right, nice problem. Let's go to the next one. All right, here's problem 3. Consider an electrical AC circuit shown. It consists of a variable frequency AC generator providing a voltage Vt equals to 28 sine of omega t, a 10 ohm resistor, a 1.5 microfarad capacitor, and a 2.4 millihenry inductor. Question 10 says, at resonance, which of the following components has its largest peak voltage across it? All right, so what we should do right here is probably calculate what the resonant frequency, it's just always kind of a nice step. Resonant frequency for this type of AC circuit is 1 divided by LC. Let's substitute in our values. So we're given the value of the inductor and the capacitor. That's pretty straightforward. 2.4 millihenry, 10 to the minus 3, and then multiplied by 1.5 times 10 to the minus 6 converted into farads. And what you get now is, I'll just do 16,666 radians per second. All right, that's our omega. Well, what is this reactance due to the capacitor? It's 1 divided by omega c. If you substitute in my resonant frequency, I should get a value here, and just did that. I get approximately 40 ohms. All right, so you see that the 40 ohms is bigger than the resistance, right? We actually have XC, which is bigger than R. That means what? That the voltage across the capacitor is going to be bigger than the maximum voltage across the resistor right here. Okay, now to compare the capacitor, the maximum voltage across the capacitor to the generator, again, many things you could do, but one thing you could just try to calculate what its magnitude would be, right? The maximum that you're going to get across that capacitor is equal to XC, the reactance, multiplied by that maximum current. And since we're operating at resonance, the maximum current here is going to be the maximum voltage across the generator, which in this case would be 28, and divided by the resistance, because we are operating at this resonant frequency right here. And you can see that XC over R is going to be a number bigger than 1. So the voltage across the capacitor is also going to be bigger than the voltage across the generator. So B is really the correct answer for this. All right, next question says, what is the peak current through the circuit when the generator is running at this different frequency right here? So for a series RLC circuit, the maximum current you're going to get is going to be Vmax divided by the total impedance. Now you could just go ahead and calculate what this total impedance is, or we could just substitute in all our values. So this will be R squared plus, now XL would be omega L, and minus the reactance of the capacitor, and I have to square that. So we have all our values. Here's our omega. We substitute the L, the C, and the R, the Vmax, which is going to be 28 in this case. And you substitute all of this, you're going to get an Imax, which is 1.58 amps. All right, and that there corresponds to choice B. All right, how about the next problem? As I say, what is the magnitude of the phase between the voltage generator and the current? Okay, so the way you calculate the phase for an RLC circuit is doing this. Tan minus 1 of, again, XL minus XC divided by that resistance. Again, I could substitute XL for omega L and XC by 1 minus omega C. It really doesn't matter. At the end, once you substitute in all our numbers here, we should get a phase angle which corresponds to like 55.7 degrees. And that there corresponds to choice C. All right, and the last question over here says, with the generator frequency still at 2 times 10 to the 4 radians per second, what is the first time after T0 that the magnitude of the voltage across the resistor is at its maximum value? So the voltage across the resistor at every single time is simply Ri max multiplied by sine of omega t minus the angle phi that we just solved for. If we want this function to be a maximum value, what you want to do is you want to set this equal to 90 degrees, or pi over 2 if you convert things to radians. That is when it's going to be equal to its maximum value. So what you end up solving is omega t minus phi equals to pi over 2. Bring the phi on the other side, divide by omega, I get my expression for time, which is pi over 2 plus the angle phi divided by omega. Now we substitute our values, so pi over 2, now plus. Now if you're going to substitute that in degrees, be a little bit careful. You have to convert it to radians, so I'm going to include this conversion factor over here, and then divide it through by 2 times 10 to the 4. I put all those numbers in the calculator. You should get 1.27 times 10 to the minus 4 seconds. And that there corresponds to choice B. Here's problem 4. An AC generator provides power for the circuit shown below. The generator voltage is described by this function, where the maximum voltage is 120. The inductor is 660 millihenry, capacitor is 180 microfarad, and the resistor is 110. Our angular frequency is 40 radians per second. What is the phase angle between the generator and the current? Okay, so what we need to do really for this type of series RLC circuit is calculate what this phase angle is given by this expression, XL minus XC divided by R. Now it helps to calculate what these reactance values are ahead of time and then just substitute it up ahead. So the inductive reactance is omega L and the capacitive one is 1 divided by omega C. We substitute our numbers here. We have 40 for here, and we have 660 millihenry times 10 to the minus 3. Put those numbers in the calculator. I think I get 26.4 ohms for this value, and for the reactance due to the capacitor, I get 1 divided by 40 multiplied by 180 times 10 to the minus 6. Put those in the calculator, I get 138.9 ohms. All right, so now we're in a position to calculate what this angle is. All right, inverse tan. Substitute the numbers here, 26.4 minus 138.9. All of this divided by the value of the resistance, which is 110. All right, I put those numbers on my calculator. I got 45.6 degrees. Now they're asking us, this here clearly looks like choice E right here. This circuit right here acts more like a capacitor than it does an inductor. More capacitive than inductive. Okay, so this circuit is being driven where? At its resonant frequency, at a frequency above its resonant frequency, or at a frequency below its resonant frequency. Well, one thing we already know is that from above, we calculated the reactance of the capacitor is bigger than the reactance of the inductor. Okay, so what would you do? Well, that automatically tells you right here that my frequency omega is actually less than the resonant frequency of this circuit. And you can go ahead and calculate what that frequency is. It's just 1 divided by LC. Just substitute our numbers and you should get something like 91.7 radians per second for the resonant frequency. But we're clearly operating below that, which is 40 radians per second. Okay, so that one is pretty straightforward. It's below its resonant frequency. Next question from problem 4 says, at time t equals to t1, the current in the circuit is 0. Okay, what is the magnitude of the voltage across the capacitor at this time? Well, if the current is 0, guess what? It means that the voltage across the capacitor is at its maximum value. Okay, that's when the capacitor ends up being fully charged. So how would you write what the maximum voltage across the capacitor is? All right, the maximum voltage across that capacitor is the reactance multiplied by the maximum current. So what we need to do now is just substitute our values here. The maximum current for this type of AC circuit, again, it's the maximum voltage that you're from the generator divided by the total impedance. And the total impedance has a resistive component, and it also has these reactive components that we need to substitute in. All right, now we know all the numbers here, so we just got to be a little bit careful. That reactive capacitance right here was 138.9 ohms. The maximum voltage of the generator is 120, and then divide by all of these terms. My resistance was 110, square that. What else? Plus 26.4, and then minus my 138.9 and square that whole term. Now be careful with the numbers in the calculator. When I did this, I ended up getting 105.9 volts. If I reduce that to two significant figures, I get a voltage that's approximately 110 volts. And that there corresponds to choice E. All right, last question for this problem says at resonance, the average power delivered by the AC generator is what? Okay, so how do you calculate average power? Again, it is simply given by 1/2, and we want to know E max, the maximum voltage of the generator, multiplied by I max. Okay, since we're dealing at resonance, guess what? Because at resonance, we have that this term goes away, right? All of the reactive components don't contribute, right? They just cancel each other out. So what you're left with is 1/2 E max, and my maximum current then is simply that maximum voltage divided by only the resistance. So this is straightforward. So this is 1/2. The maximum voltage was 120, square that value, and now divided by only the resistive component, which is 110. All right, you go ahead and you substitute the values. We should get an average power that looks around like 65.5 watts. And that there, folks, corresponds to choice B. All right, let's go to problem 5. All right, problem 5 says an LRC circuit has an inductor of 34 millihenry, a capacitor of 16 microfarad, and a resistor of 11 ohms. The AC generator is supplying a maximum voltage of 60 volts at a frequency or an angular frequency of 433 radians per second. First question says the current through the resistor, blank space, the voltage across the generator. So they're looking for the relationship. Does the current lead or does it lag or is it in phase with the generator? Well, it's definitely not going to be in phase. I don't think so, but let's just calculate it just to be sure. So one thing I would do to determine this is you calculate what these reactance values are for the capacitor and also for the inductor. All right, if we go ahead and we substitute our numbers here, we should get 433 for omega, and the capacitor was 16 microfarads. All right, that gives me a reactance for that capacitor of 144 ohms. We're also told that we have 433. The inductor value was 34 milli times 10 to the minus 3. Substitute that, I get a reactance for that inductor equal to 14.7 ohms. All right, so right away we could see that XC is bigger than XL. So this tells me that this circuit acts more like a capacitor than it does an inductor. Okay. So what does that mean? One thing to remember about AC circuits is this kind of cool little trick is Eli the Iceman, right? Eli the Iceman. And this tells you what leads what in AC circuits. If it behaves more like a capacitor, I'm focusing on this part over here. And this says that for a capacitor right here, that the current is ahead of the voltage. Okay, whereas if it was more inductive, we would have that the voltage, which we use the letter E for, is ahead of the current. Okay, but we're looking at the second case over here since it's more capacitive. So the current here should lead the voltage across the generator. All right, so that is this one right here. Next question says the current through the inductor, they compare it to the current through the resistor. All right, well, since this is a series circuit, one thing we need to know is that the current is the same everywhere. Right? Doesn't matter if you're looking at the generator, the inductor, okay, through the wires, is that it is in phase everywhere. Right? There is no phase difference between the currents in the various elements. All right, next problem says, what is the maximum current through the resistor? All right, well, the maximum current through the resistor is simply given by the maximum current anywhere. I can calculate that as being V max divided by the total impedance of this circuit. So here we have V max divided by since it's a series AC circuit, my impedance is given by this, XL minus XC. We've seen this so many times now. Now we substitute in our numbers. I have 60 volts for the peak. I have a resistor, which was 11 ohms, square that. And now I've already calculated both of these reactance terms, so now it makes it easy just to substitute it inside here. So we get 14.7 minus 144, and square that term. All right, put all those numbers in the calculator. I think I get something like 0.46 amps, and that there corresponds to choice A. All right, next question here says, in order to increase the maximum current in the circuit, the frequency of the generator should do what? Well, remember, when do you get the maximum amount of current? Is when you make the impedance as small as possible. So we get that whenever we're operating at the resonant frequency. So what would be the resonant frequency of the circuit? It's always given by LC. We know the value of L and the value of C. We just substitute, and those values give you a resonant frequency of 1356 radians per second. Well, guess what? If I compare it over here to the 433, that means I would really have to increase that frequency of the generator in order to approach resonant behavior of the circuit, and that's where I would maximize the amount of current that I would get. All right, that's it for this problem. Let's go to problem 6. Problem 6 says an RLC circuit has maximum voltage across each component given by the maximum voltage across the inductor is 440, across the capacitor it's 373, and across the resistor it's 173. And the resistor has a resistance of 6 ohms. All right. First question says, which of the above represents the phasor diagram for this circuit? So let's have a look at where we are. So we have VL, that is along the positive y-axis. Now, one thing we should know is that VR, if we're going to have this, VR should look like this. That you can't have VR at some angle like this. That one doesn't make sense. So I think that is really all we have to do right now. The other thing we know is that the voltage across the inductor is bigger than the capacitor. So in this case here, we should have that. Let's just write that down. This should behave more like an inductor than it does a capacitor, okay? And one thing for inductors, again, if I go back to my Eli the Iceman, a little trick over here. If I'm looking at something that is more inductive, I should have that voltage leads the current for this type of circuit. So let's go see it, all of these choices. Here we have that the voltage of the generator is over here. And then we have that the current, well, the current is also in phase here with the voltage across the resistor. These here would also be kind of the phasor of the current would also be along this positive x-axis. So here you can see here, in fact, that the voltage does in fact lead the current, so that there would correspond to choice B as being the correct answer. All right, last question says, what is the average power dissipated in the resistor? All right, well, my average power dissipated in the resistor, you can write as 1/2. What is the maximum voltage across that resistor multiplied by what is the maximum current going through that resistor? Maybe I could just simply write it like this, VR max. And that maximum current across the resistor is, well, what is the maximum voltage across the resistor divided by the total resistance? Okay, so this simply simplifies to the maximum voltage across that resistor divided by the value of the resistance. Pretty straightforward. We get 1/2. VR max, I go up here, was 173, and I square that value, and now I divide it by that resistance of 6 ohms. Put all those numbers in the calculator, I get like 2,494 watts, and that there, the best choice would be choice A. All right, folks, that's it for me. Thanks for watching. We'll see you next time.